some math. So from Monday, so what do we have from Monday? We talked about the end behavior. So basically, even degree polynomials act like and odd degree polynomials act like cubics. Right? We're back in the long run. So that's our little end behavior. We also discussed the concept of multiplicity. What is going on over there? Did I just jump into that too early? Yeah, do you need another minute? Oh. I'll give you all another minute. I don't think even and goes through if it's odd. So even bounce off. The x-axis and odd cross the x-axis. So for example, if I give you this function, I'm going to just kind of more review of what we did last time. Something like 1 minus x, and then x plus 2 squared, and x minus 3 cubed. And I want us to sketch this thing. We'll like it when things are factored. It makes it easier for us because we have a connection between factors and zeros and intercepts. There was another concept from Monday that there's a connection between factors, zeros, and intercepts. They all mean the same thing. Whatever your factor is gives you the zero, gives you the x-intercept. We talked about that. So just by looking at this polynomial, what is the degree of this polynomial? Are you sure? 6. Because you have 2, 5, and then there's one more. So that's 6, right? There are a total of 6 x's. So this is a 6-degree polynomial. And the leading coefficient is going to be positive or negative. Are you sure? Yeah, but the first parenthesis has negative x, right? Doesn't have to be, but think about this. If I square this, that gives me some kind of an x squared, and that gives me an x cubed. But then I'm going to multiply by negative x. So that's going to give me a negative x to the 6th power. So leading coefficient here is negative. So we know the end behavior. It's an upside down parabola, right? So all even degree polynomials act like quadratic. So negative leading coefficient and upside down parabola in the long run. So that's what we kind of did on Monday. Now let's list all the zeros and their multiplicity. So what are the zeros here? What are the zeros of this function? 1, 1, -2, and 3. And what is the multiplicity of 1? 1 and negative 2 and 3. And we know that just by looking at the exponents. So x equals 3, the multiplicity is the power. Not just, they kind of seem to be lined up almost perfectly. It's a coincidence that the numbers are the same. So the way we're going to graph this thing, so we have negative 2, positive 1, and positive 3. So we start on the bottom using our end behavior. What's going to happen at negative 2? And we're going to go through or bounce off. Bounce off. Then I need to turn around, hit 1. What's going to happen at 1? Go straight through 1, and then turn around and hit 3. What's going to happen at 3? Yeah, do like a little cube, right? So what we agreed on that the way the graph intersects the x-axis is basically each one of those separate functions. And if you just think of x plus 2 squared, that's a parabola 2 units to the left. If you're thinking of x minus 3 cubed, that's a cubic squiggly thingy 2 units to the, 3 units to the right. The fact that leading coefficient is negative makes them upside down, but that's not that big of an issue. Is that okay? So my phone is on. Turn it off. Yeah. Questions? So that's from Monday. Yeah?
So why did it bounce off negative 2?
Well, we're just basically going by this little power. If that power is even, it's going to bounce off. Okay? So we did that on Monday, and then basically, again, just think of this function separately. X plus 2 squared, that's a parabola, so locally, you're getting a little parabola there. It's kind of a way to remember what's going to happen. Okay? But I want to make another connection. I want to paraphrase this multiplicity concept, the one that we did on Monday. If I look at this function around 2, around negative 2 rather, what are the signs of this function? Is the function positive or negative here? What? Yeah, this little chunk. Why? Yeah, but that's not. So what? How does that? Yeah, as she said, but what is the value of the function here? Is it positive or negative? Yeah, negative. The y value is a negative, so the function is negative, 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 and then it's still negative, right? Yeah, it's going up, but that's not what I'm asking. I'm asking what is the value of the function? Negative. How about here? And then what? After I pass that intercept, it becomes positive, right? Went from negative to positive, and then it goes from positive to negative, right? So we can make a prediction. If I look at a 0 of even multiplicity, the function does not change the sign at zeros of even multiplicity, while at zeros of odd multiplicity, the sign of the function changes from negative to positive or positive to negative. This will be very useful when we're going to start solving inequalities. This little idea will save you a whole lot of time. Your book will get all medieval on you how to do those inequalities. And when you do help me solve this example thing, it's just going to be very confusing. So, but this is the good stuff. If you just understand the concept that at even multiplicities, the signs do not change, and at odd multiplicities, the signs do change, this will help us tremendously down the road. So I'm going to make this a little rule. So the sign of f of x stays the same around zeros of even multiplicity and the sign of f of x changes around zeros of odd multiplicity. Okay? And again, this makes sense because even multiplicity, the graph bounces off the x-axis, so it stays on the same side of the x-axis, meaning the values of the function have the same sign. While odd multiplicity, you cross the x-axis, so you go from negative to positive, from positive to negative. This will help us later on. Important rule. Probably not in the book. We're kind of interpreting what's in the book for our, guilty pleasures here, because this will help us later. But does the rule make sense? It's just basically paraphrasing the multiplicity concept. Okay, so that's basically a section 4.2. So we're not going to talk about 4.3 and 4.4. I put the lecture notes and the videos on Canvas from those sections. So if you want to, do the extra credit, you can watch the lecture recordings and read the notes if that's going to help with the homework or whatever, if that's what you want. But anyway, so section 4.5, rational functions. And so basically a definition of a rational function, f of x equals p of x over q of x, where both p and q are polynomials. So you have a polynomial in the numerator and a polynomial in the denominator. No square roots, none of that nonsense. Where p and q are polynomials. So then domain of this function, the only problem that can occur here is division by 0. So the domain would be all real numbers as long as q of x is not 0. Just the way the q of x is written. There's no mentioning of reduce p and q first or whatever. Just whatever you see, as long as the denominator is not 0, we're good to go. So for example, if I give you this little function, and I ask you, well, first of all, is that a rational function? Yeah, they're, polynomial on the top, polynomial on the bottom. What is the domain of that function? Is that it? And negative 2. So one thing you should get used to or accustomed to be doing every time you see a function is to start factoring things. Because when things are factored, you get lots and lots of information, especially since we already know that factors and zeros, there's a big connection between them. So yeah, so domain of this function is all reals except for plus or minus 2. Okay? But that means all other real numbers will work. I can take any real number except for these two, plug them into the function, and get a real answer. Right? That's the concept of the domain. So that means I can get as close to positive 2 as I like. I can plug in 1.9 and 1.99. and 1.79s. I can plug it into this function, and I'll get a pretty answer. Okay, I take this back. I'll get a real answer. But can we guess what that answer is? Just pretend putting a number close to 2. I'm going to start talking kind of in abstract notions here. If I put something close to 2 for x, so x squared will give me something close to 4, and I add 1 to it, so I get something close to 5 in the numerator. So are we happy with that? So numerator is close to 5 as we're approaching these fancy numbers. While in denominator, as x gets closer to 2, close to 2 squared is close to 4, close to 4 minus 4 is virtually 0, right? Well, let me ask you this. Basically 5 divided by something really, really small, almost close to 0. What kind of answers are you going to get? Small or big? Big, right? If your denominator is small, if your denominator is almost 0, the ratios will become almost infinite. So the values of the function go haywire as we approach these two magic numbers. Who is buying what I'm selling right now? I made a quarter last time I told this class earlier. I was selling it so hard they gave me a quarter. So we'll see what you're going to give me. But, ooh, that's not what I want. It's all right, quarter, that's what, apparently. Okay, well, this is already kind of. Okay, so what I have here, I don't know, you don't need to know Excel, but I just typed in that function. Something squared plus 1, that's the numerator. Something squared minus 4, that's the denominator. So I just have to put in the values for x, and it will give me the values for y. So if x equals 1, y equals negative 2/3, apparently. Okay? So I'm going to start putting numbers that are close to 2. So things like this, 1.99, 1.9999. And when I copy this, see what happens to the y values? I mean, where are we at? Negative 12,000 and basically 500. And if I keep going, what is that? Yeah, it rounded it to 0. I have to be careful with Excel. Here we go. Yeah, you see, it doesn't even get it. Anyways, but I can do it on both ends. Stop it. What? Sorry. What if I do from the other end? If I do like 2.5, what happens there? 2.1, 2.01, 2.001. So what happens on the other end? See, here I was getting large negative numbers. On the other end, I'm getting large positive numbers. See that? So, like, well, what does it look like graphically if I try to represent this concept with the graph? Here's that 2. Stop looking 2. So as I'm getting closer and closer to 2, the values are becoming large and negative. So the function takes a dive as it gets closer and closer to 2. It doesn't get all the way to 2. There is kind of a force field of sorts. It cannot get to 2 because then you start dividing by 0 and things get bad. But as long as you're to the left of 2, the function tanks. On the other side, when you're to the right of 2, the values of the function go to positive infinity. So the function does this weird kind of a split at that number. But it never really gets to that. There's this kind of an invisible wall that protects that number. Some of you know what that little thing is called. What is it called? Yes, that's called an asymptote. And it's a vertical asymptote because it's a vertical invisible line that your function doesn't quite get to. Your calculators will have problems and difficulties with asymptotes, I think. At least I hope that your calculators are so weak and they cannot comprehend that you should kind of skip over the value. Things you might draw a vertical line in there, which is not good. But this is what's happening around um, that number. Okay. Comments? Sure. That's good. If that made sense. Okay, good. So then use that. So yeah, that's the second street. That's right. Um, so we call that concept, this idea, is called the vertical asymptote. And basically, the way you find the vertical asymptote is pretty simple. The first step is to reduce your function. So there's a difference between finding the domain and finding the asymptotes. For the domain, the function is the way it's written. For the asymptotes, you want to reduce that first. And second step, just zeros of the denominator are the asymptotes. And we'll just abbreviate VA for vertical asymptotes. So this function has two vertical asymptotes, one at positive 2 and one at negative 2. Now the way those asymptotes behave, the way the function behaves around the asymptote, that's a whole different issue, and we'll deal with that momentarily. Okay, so I want to now try and sketch the graph of this function, see what we can do. But does it make sense what a vertical asymptote is? Basically, not precisely what's not in your domain, but after you reduce your function, whatever's left in the denominator, those are the vertical asymptotes. So let's try and sketch. So again, your first urge is always to factor everything. There's nothing I can do about that numerator, but I can definitely factor that denominator. Now, as a general rule, every time you're trying to graph something, it's always good to find the intercepts, the x and y intercepts. So we'll be doing that. The first step will be to find the intercepts. So first find the x-intercepts. And how do we do that for any function? I'm not sure what I'm trying to do in that corner, but how do we find x-intercepts? Just the general idea, regardless of what a function is. Right. Set y equal to 0. That was the thing that you were taught, right? Set y equal to 0. So we're making our, whatever the function is, we'll set it equal to 0 and we're trying to solve for x. Now, the function happened to be a fraction. The only time a fraction can be 0 is when numerator is 0. So denominator is irrelevant if it's a fraction and you're trying to solve it for 0. So really, when you're looking for x-intercepts, you're looking for the zeros of the numerator, for real zeros, because the imaginary zeros don't matter. We don't see them on the graph. So does this thing have any real zeros? No. So no real solutions. Meaning no x-intercepts. the y-intercepts. Again, from way back, to find the y-intercept, you're going to set x equal to 0. And so for y. Right? Now, it's really easy to do with this function. Really, all you have to do is just to cover your x's. That I just said x equal to 0. What's left? What? Yeah, negative 1/4. That's what's left. So the y-intercept is y equals negative 1/4. Okay, so we have this much. I can start graphing this function. So no x-intercept, little tiny y-intercept of negative 1/4. So the function goes through that point. Okay? So the first step to find intercepts. The second step would be to find the asymptotes. So vertical asymptotes, in this case, we kind of already talked about this. You factor a function, you try to reduce it, nothing to reduce. So whatever zeros of the denominator, those are your vertical asymptotes. So x equals 2 and x equals negative 2. These are the two vertical asymptotes, whatever sets your denominator to 0. Basically the domain, whatever we excluded from the domain. But be careful, because domain you don't reduce, for asymptotes you do reduce. Nothing to reduce here, so same thing. We're okay with those two being our asymptotes? Is that all right? So on the graph, they look like this. So I can already start sketching the graph of this function. I can sketch the middle, because I have to hit this point, and then I have to, what I'm from now on going to call respect the asymptotes, meaning you have to either dive in front of an asymptote or go up in front of the asymptote. So how can I do that? How can I go through this point? And now how many options do I have really? Two. What are they? Like that? So there's only one correct answer. But yeah. Very good. I don't have any x-intercepts, right? So out of the 4 options that were just mentioned, now here's one option. Not good, just cross the x-axis. There are no x-intercepts, right? It'll go away. Here's another option, still not good, creating an extra intercept. Here's another option, still not good, creating 2 x-intercepts. So the only thing that can possibly work is the upside down parabola here. Well, parabola looking thingy. It's not precisely a parabola. So we approach the asymptotes, we're not creating new x-intercepts, and we're not touching the vertical asymptote. No matter how much you want that to happen, you can never touch a vertical asymptote. We're going to have other types of asymptotes that, you know, we can disrespect here and there, but not the vertical ones. Vertical ones meaning you just started dividing by 0 if you touch it, and that's not good. Okay? How is that? There is another fun fact that can help us. Is this function odd or even? Even, right? If you do the quick test, you plug in negative x, all the negative signs go away, so the function is even. Well, therefore, you got to have a symmetry around the y-axis. So those cubic-looking things were out of the question, because they do not give you that symmetry. So you can always use that as an extra check. The even functions will be symmetric around the y-axis. So really, I just need to figure out what happens to the right of this asymptote, then exact same thing will happen to the left because it will have that symmetry, right? How are you doing so far? Is it making sense so far? Here's another big piece of truth that I'm going to tell you that's not in the book. And this is what I'm starting to sell you concepts. Remember how we just mentioned how zeros of odd multiplicity, the function changes the sign at zeros of odd multiplicity, and the function stays the same as far as the sign goes around zeros of even multiplicity? Remember we wrote that down as a rule? Well, the same thing happens around the asymptotes. If you have asymptotes of odd multiplicity like here, the sign will change. And we saw that, right? When I was plugging numbers, I was getting negative infinity on one end and a positive infinity on the other end. So if you have odd exponents in those denominators, you'll have this kind of behavior. If, let's say, this one was squared, then it'll look like that. So it'll be on both on the negative side. So if you have odd multiplicity with asymptotes, same thing happens as with zero, so the function changes the sign. Okay, so we have this little chunk. Now, can this happen? Why not? Right, I shouldn't be creating new x-intercepts, so good. So that means this can happen, right? This can happen, right? The function can fly out to infinity, or maybe function will start evening out or evening out at the x-axis or something like that. The function might start flattening out at some point. So we need to make a little experiment and see what happens to the value of the function for extreme values of x, for large values of x, or for small values of x. So we need to learn how to literally substitute infinity in for x, which is impossible. We cannot do that. But we can certainly think about it. Are you ready to do some thinking? Alex is not happy about that. He made a face. But let's try this. First of all, I'm going to make a little statement that so let r be a positive number, then a, where a is any number, over x to the r will go to 0 as x goes to infinity. Positive or negative infinity for that matter. Now think about this statement. I have a fixed numerator, no matter what it is, just some constant, no matter how large it is, doesn't matter. And then denominator, that's where the variable thing happens. And I'm letting my x to get infinite, larger and larger and larger. So now, regardless of what the value of r is, if x is getting larger, then x to the r is getting larger, right? Are you buying that? So if you have something that's fixed, a fixed numerator, divided by something that keeps getting larger and larger and larger, that ratio will eventually become almost 0. Not identically 0, but pretty darn close. Are you buying that? Okay. Yeah? Because I'm about to do some crazy math. But you have to be pretty comfortable with that statement. Let me play with Excel, if you don't mind, just to maybe convince you. I'll do the same kind of table, x and f of x. So what should we put in the numerator for a fixed number? Do you have a favorite number? 7. Okay. So I'm going to make my function to equal 7 divided by x. Any favorite positive numbers for the power of x? 2. But again, doesn't have to be a whole number, could be a fraction, as long as it's positive. How about 0.2? Would you like that? A little weird. 5th root of x, that's what it is, right? So, you know, when x equals 1, then we'll get 7, because the denominator is 1. But I'm going to increase the x and then see what happens to the values of the function. You know, the general pattern is what? It gets smaller and smaller, so eventually I make it large enough. Yeah, exactly. But if I kept it at 2, it'll get to 0 a lot faster. I mean, those are all zeros. Right? It's a 42 zeros after a decimal. Okay, so we're happy with this? Now I'm going to do a magic trick. No, I don't need this. I need something to write with. Okay, here we go. So here's my little function. And I'm going to try to figure out what happens to the values of this function as x getting larger and larger and larger. So I'm going to ask you this question. What is the largest exponent that you see in the denominator? 2. You agree with that? So I'm going to do the following. I'm going to multiply this function by 1 over x squared over 1 over x squared. Is that a legal step? I multiplied by 1. The reason why I chose the square, you just answered that, the largest power in the denominator. If the largest power in the denominator was 7, then you can go 1 over x to the 7th, 1 over x to the 7th. So now we'll do some distribution here. What is x squared times 1 over x squared? 1, okay. And then 1 over x squared times 1 is, well, 1 over x squared. And then I'm going to do the same thing here. 1 minus 4 over x squared. Okay? So I just rewrote my function in a funky kind of way. It's the same function, really. Okay? But then see what happens now. So we will let x just fly away to something large. What will happen with 1 over x squared as x gets larger and larger based on that little thing? What's going to happen with the values of 1 over x squared as x? Yeah, it will basically become irrelevant. It's almost 0. What about this guy? Also 0, right? But 1 is 1 and 1 is 1. Nothing happens to those two. They're not being affected by x. Right? Those are constants. So what's left if those two things virtually go to 0? What is left? 1, right? 1 over 1, which is 1. So that means the values of this function get closer and closer and closer to 1 as x gets large. Let me show you this. If I go back to my function, I start plugging in large numbers. See what happened to the y value? You know, I just plug in large numbers, the y value, okay, 1. It's a rounding error. If I put in large negative numbers, it's still 1. Okay? So for large values of x, the function starts evening out at 1. Okay? So that is a horizontal asymptote. Graphically speaking, this will happen. We'll have a little horizontal asymptote at 1, so the function will flatten out like that. So on the other side is just the mirror image, using the symmetry or the fact that there are no x-intercepts, so it has to be on the top. So that's the graph of this function. So horizontal asymptotes become important as well. And they really kick in for large values of x. You can cross a horizontal asymptote for small values of x. Nothing bad happens. You're not breaking any rules by crossing horizontal asymptote, but they really kick in for large values. Vertical ones, never. Okay? So, did you like that? Was that pretty? Okay. What? Oh, I don't know yet. It's definitely on a test, but I don't know if it's gonna make an appearance on your future exam here. But so here's some definition for vertical and horizontal asymptotes. So, vertical asymptote, if f of x goes to positive or negative infinity as x approaches a, then x equals a is a vertical asymptote. Because remember, vertical asymptote is some fixed number on the x-axis at which your function starts going crazy. So things start flying to positive or negative infinity. The horizontal asymptote, y equals a is a horizontal asymptote if f of x approaches a as x goes to positive or negative infinity. So it's kind of the opposite. Now the function approaches a number as you travel outwards on the x-axis, left or right. So these are some definitions of that. Do the definitions make sense? So I want to do an example where we're going to graph a function. But basically, here the steps will follow like that. First, find the intercepts. I mean, factor first. That's of course. That's no matter what you're going to factor first. Find the intercepts, find the asymptotes, and then kind of try to reason where the graph should go. Don't create new intercepts. Remember how the signs changes around odd multiplicity, stays the same around even multiplicity. Because your book goes kind of a little off in that subject. They'll start plugging in points and see whether the graph is above or below. You don't need to do that. Usually if you have at least 1 point, and usually do have at least 1 point, then you can go from there. Sometimes you don't have a point. Sometimes you don't have any x and y intercepts. Oh well. Then you have to plug a point and see what's happening. Let me take an example that we did with another group. Let's see. I don't remember the function that we played with. Oh yeah, let's try that one. X minus 2. So f of x equals x minus 2 over x squared minus x minus 12. So here's the function that I want to try and sketch the graph of. So first I will factor, because this will help tremendously. How do you factor the denominator? Very good. So there we go. So we factored that. Nothing cancels, so we already see our vertical asymptotes. Whatever make the denominator equal 0, those 2 points are vertical asymptotes. But first, intercepts. So the x-intercept, zeros of the numerator. So what makes that numerator equal 0? 2. So x equals 2 is the x-intercept. The y-intercept, cover all the x's. What's left? 1/6, right? It's negative 2 over negative 12, so it's y equals 1 over 6. You know, you're setting x equal to 0, so you're only left with constants. So I can start sketching the graph of this thing. So 1/6 is right here, and positive 2 is right there. Here are my 2 intercepts. Second step is to find the asymptotes. So the vertical asymptote is just whatever makes the denominator equal 0 after you factor and reduce. So we only have 2x equals 4, x equals -3. So these are my two asymptotes. So here's 4, and here's -3. So we already know what's going to happen in the middle. We can sketch the middle part. There's only one option. There's only one way you can connect these 2 points without creating new x-intercepts and respecting the asymptotes, showing the proper asymptotic behavior, right? You see that there's only one way that can be done. You have to connect these 2 points and then go up and then come down. Because again, the way I know that it's not going to bounce off 2, because 2 has multiplicity of 1. So every time you see zeros or asymptotes of odd multiplicity, the sign will always change. So the sign of the function went from positive to negative, right? And also, when you pass the asymptote, is my function going to be on the bottom or on the top? What do you think? Is it going to go like that or like that? Based on what I just said 12 seconds ago, how do we know this option or that option? So every time you have zeros or asymptotes of odd multiplicity, the sign of the function changes around those zeros or asymptotes. So what is the multiplicity of this asymptote? And 1, right? There are no powers. So therefore, the sign of the function has to change. It has to go from negative to positive. So it has to start from the top. So the sign changed. But again, we don't know how it's going to even out or whatever. It's definitely not going to cross the x-axis again because there are no there are no more x-intercepts. But we don't know what's happening here, so we need to find the horizontal asymptote. So we'll do it again this borderline psychotic way. Again, we're going to look at this expression, and you're going to ask yourself, what is the largest power in the denominator? What is the largest power in the denominator? 2, so we'll multiply by 1 over x squared, 1 over x squared, and we'll distribute. So when you distribute that, 1 over x squared times x is just 1 over x. One of the x's canceled. And 2 times 1 over x squared is -2 over x squared. And we do the same thing in the denominator. X squared times 1 over x squared gives me 1. Negative x times 1 over x squared gives me -1 over x. And then times 12 minus 12 over x squared. So basically, I am dividing each term in my function by x squared. That's what just happened. That's what I did. Now, what's going to happen with 1 over x as x goes to infinity? What's going to become of this? Yeah, it gets closer and closer to 0. This gets closer to 0. That gets closer to 0. That gets closer to 0. That's a constant. That's 1. So really, we're ending up with something like 0 over 1, which is 0. So the horizontal asymptote is 0. So that means the function flattens out at the x-axis. It gets really, really close to the x-axis in the long run. So the way I graph this, I have to do this, right? On the left, do I go from the top or from the bottom? What? Bottom. Why? No, there's no symmetry. It's all ugly. But why is it, you're right, it's like that. Why is it like that? How do I know that? Yeah, it's the odd multiplicity, so positive, negative. Has to be opposite signs. Which your book is going to make you do that, and beware of that. That will ask you, pick a number to the left of -3. Can somebody do that? That's to the right of -3, to the left. -7. Then take -7 and substitute this into your function. -7 minus 2 is something negative. -7 minus 4 is something negative. -7 plus 3 is something negative. Negative divided by negative times a negative is negative. Therefore, we're going to be below the x-axis. And then pick a number to the right of +4. 7. 7 minus 2 is positive. 7 minus 4 is positive. 7 plus 3 is positive. Overall, positive. So above the x-axis. So they'll make you do that almost on every interval. Or you can just say, well, we got the middle for free, and then do this odd multiplicity, change the sign, odd multiplicity, change the sign, so you don't have to test any intervals. Which you can do, by the way. That's a proper technique, but this is fancier and quicker and more fun, if that makes sense. So odd multiplicity, sign changes, zeros, asymptotes. So everything, -3, +2, and +4 all had odd multiplicities, and the sign changed. It went from negative to positive, from positive to negative, from negative to positive. The sign of the function changed at each step. How's that? With another group, here's the graph of this function, x minus 2 divided by x squared minus x minus 12. Using foo plot, is that pretty much what we just did? And you see what happens? As I travel further and further, the function gets closer and closer to the x-axis, but it never touches it. I can go further and further out. It will keep getting closer, but I'll zoom in and it will still be a gap. There's always going to be a gap between the x-axis and the function, but that gap will keep on shrinking, shrinking, and shrinking. Is that okay? So these are your asymptotes. Yeah, here we go. And these are your vertical ones, +4, -3. Now notice how on this example, we crossed the horizontal asymptote, right? X-axis horizontal asymptote, we crossed it, that's okay. You can cross horizontal asymptote for small values. Horizontal asymptote only matter for large values. Vertical ones, you can never do that, because that's division by 0. Horizontal ones is more of a guideline. They can be crossed and touched or whatever. Vertical ones, stay away. That's your 2nd Street in Detroit. Is that right? Is that the thing you want to stay away from? Okay. All right. So, but you might survive the 2nd Street in Detroit, unlike the vertical asymptote. There we go. So, even worse. Okay. Now, how did you like that whole process of finding the vertical asymptote? This little fun part, wasn't it fun? Oops. This little, the process of dividing by whatever, or you like that? No, you shouldn't. This is hard. This is hard. This is hard to do. So there's a better way. There's another pattern that I'm selling to you. I made a quarter off of that pattern with another group. Okay? But this is the good thing, because that will really going to save it. This is the hardest part of what I just did, finding the horizontal asymptote. But if I just pay closer attention to this function, where I got 0 for the answer, right? This one right here. Horizontal asymptote is 0. Again, horizontal asymptote only matters for larger values of x. And this function was really a linear divided by a quadratic, right? Linear by a quadratic, so it's small divided by big. As x gets bigger and bigger and bigger, it's a linear divided by a quadratic. It's 1,000 divided by a million. It's 1,000,000 divided by, I don't know what million squared is, 1,000,000,000,000. Those are small numbers, right? So every time the degree of your denominator is bigger than degree of the numerator, the horizontal asymptote will be 0, because this is small divided by large. That's 0. The other way around, if the degree of the numerator is larger than the degree of the denominator, so it's large divided by small, that's still large. So that will go to infinity. It will not have an asymptote. It will just keep growing and growing and growing.
Integral of x squared is x.
That, first of all, that's not true. And yeah. But that's not true, because make sure you understand that that's false, because you will remember this for many years. And it will stick in your head that integral of x squared is x. That's not true. Yes, he was actually my student some time ago. Of course, I don't know his name, but that's... well, he wanted to share with you the integral of x squared. That's false. The integral of x squared is not x. It's x cubed over 3. The integral of x squared is x cubed over 3 plus a constant or whatever, but it's not x. Just, you know. All right. Anyways, what was I talking about? Small over large is small. Large over small is large. But if the exponents are equal, and this is what we saw here, in this case, the degree of the numerator was the same as the degree of the denominator. In this case, what was it? It's right there. In this case, the asymptote came out to be 1, if the degrees are the same. But now check this out. If I put 4 in here and 5 in there, so that means this will be 4 and this will be 5. So the answer will be 4/5. Right? Because those numbers don't cancel. And so if the degrees are the same, then the horizontal asymptote will just be the ratio of leading coefficients. That's how we're going to remember that. So there are going to be 3 cases. Top is smaller, 0. Equal, ratio of coefficients. Top is bigger, you get infinity. So let's write it all down. So horizontal asymptotes. So f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1. I'm just writing a general polynomial function, so don't freak out. Is that okay? Remember from Monday, that's a polynomial. Constants and exponents. Now denominator, some different polynomials. So I'm going to use different constants and different letters, if that's okay with you. So again, all the b's, those are just constants, and m is some natural number. So every polynomial is really of this form. So then 3 things can happen. 1, if n is less than m, meaning degree of the numerator is less than degree of the denominator, so it's small over big, then the horizontal asymptote is y equals 0. Right? Small over big, y equals 0. In the second case, if degrees are equal, so then we're just left with ratios of leading coefficient, whatever those 2 numbers are. So then horizontal asymptote is y equals a sub n over b sub m, ratio of leading coefficients. If the degrees are the same, meaning both functions grow at the same rate. You put 1,000, you'll get a, 2,000 over 3,000. You put 1,000,000, you get a 2,000,000 over 3,000,000. So that ratio stays the same. And finally, if degree of the top is bigger than degree of the bottom, so big over small, then horizontal asymptote, there is no horizontal asymptote, so sorry, show no horizontal asymptote. Okay? So we can use this so you don't have to do that division and all that fun stuff. There we go. Sorry, I'll get back to that. All right, let's do this one. 3x squared minus 12. So 3x squared minus 12 over x squared minus 1. And I'm going to do this one fast. First of all, it's always good to notice that that's an even function. If you replace x with negative x, nothing changes. So therefore, it will have symmetry around the y-axis, and it really helps when you do these types of problems. If you know the symmetry, it helps. But it just, it's not a necessity, but it's certainly an advantage. So again, I'm going to factor this thing, pull out a 3, x squared minus 4, x minus 1, x plus 1, and then 3 times x minus 2, x plus 2, x minus 1, x plus 1. So this is the whole thing factored, right? This is a simple part. So intercepts. For x-intercepts, zeros of your numerator. So that's just plus or minus 2. Whatever makes a numerator equal 0, those are the x-intercepts. The y-intercepts cover the x's, and then you're left with a negative 12 over negative 1, so 12. That's the y-intercept. Is that okay? It's really easy with rational functions. Numerator gives you the x-intercepts, and then ignore all the x's. They'll give you the y-intercept. So let's say that's 12, and this is negative 2, and this is positive 2. Okay, so these are my intercepts. The asymptotes, vertical asymptotes. What are the vertical asymptotes of this function? One or negative 1, zeros of the denominator. So x equals plus or minus 1. So here's 1. Here's 1. Negative 1, sorry. These are my two vertical asymptotes. How about a horizontal asymptote? 3. Degrees are equal. It's a quadratic over quadratic. So you're just taking the ratio of leading coefficients, 3 over 1. So yeah, y equals 3. I have enough to sketch the graph of this function. I can really do any part of it. Just think about this. Since I'm standing on the right side, I have to hit 2, and I have to stay within asymptote. So there's only one way that can be done, right? There's only one way that I can accomplish that. What about the middle? Yeah, parabola going up. I cannot go down because I'll hit the x-axis, and there are no intercepts. So this is the only option. And again, keep in mind that we already agreed that the whole thing will be symmetric around the y-axis, so that helps. But it's, again, we don't need it here, because I know the only way I can do the left side hit -2 and stay within asymptotes is that. So that's basically the graph of this function. Right? And we're done. So just operating with the intercepts and asymptotes gives us mostly everything that we need. We don't need to plug any extra points. We just keep the simple rules in mind. Do not create new x-intercepts. That's a no-no. Right? Respect the asymptotes. They're like magnets. They attract the graph. What else? You know, alternate the sign around the asymptotes and zeros, so odd multiplicity, right? See what's happening? From positive to negative, from negative to positive, right? Then again from positive to negative, from negative to positive. So the signs alternated throughout. All right, good. And of course, the integral of x squared is not x. Just making sure you don't get that stuck in your head.